Welcome back to Computer Science Theory. This is COMS W3261, offered Summer B 2021 at Columbia University. And this is Lecture 6, Part 1, review of context-free grammars, and introduction to Chomsky Normal Form. I want to start us off with a teaser to kind of remind us where we were. Last time we talked about context-free grammars, this new way of generating languages, this new way of describing languages. We talked about some of their powers. We talked about the context-free languages, the class of languages described by context-free grammars. So here's a teaser designed to bring back a few of the things we talked about last time. Question is the grammar that I'm about to write S to AB or BA, A to 10A or 1A or empty string, B to 01B or empty string, ambiguous. So some of these symbols may still be a little bit unfamiliar. We'll go through a reminder of what these things are, but I'm going to pause for 2 seconds here. If you're watching the video, you can pause it and think about this and think about either solve it, think about how you might solve it, or think about what things would you need to understand to be able to answer this question. So here's my pause. Now, all right, let's answer this question. So we have here a context-free grammar. If you remember last time, context-free grammars are composed of variables. They're composed of terminal symbols. They have a set of rules, and they have a start symbol. If you write them out formally, that's a for tuple. But you can also just write out the rule set. So if you write out rules like this, we always assume the top left symbol is the start symbol, and we read the derivation rules from left to right. So we read S arrow AB as at any time I'm allowed to take a variable S and replace it with the string AB, that string of variables. Remember that this notation, this bar notation, abbreviates two rules. So if I write AB bar BA, that's just shorthand. I'm really writing two different rules. I can take S and substitute it with AB, or I can take S and substitute it with BA. So hopefully we're caught up on how to read this grammar. We'll start with S and we'll repeatedly substitute things to derive a final string. We're done when all the variables are gone and they've all been substituted for terminal strings. So that's the grammar. Next thing to understand to solve this problem is the word ambiguous, which we discussed last time, but we just did it briefly at the end. If you remember, we say that a string is derived ambiguously if it has two or more parse trees, or equivalently, meaning this is the same thing, if it has two leftmost derivations. So a parse tree is just a way of writing down a derivation as a picture. So to draw a parse tree, we always start with the start symbol, and then we move from top to bottom following the derivation rules. So for instance, I could start with S. I could use the rule S to AB to get me two more branches, and then I continue to substitute variables until I reach terminals at every leaf of my tree. So for instance, I could use the rule A to 10A. I could use the rule B to empty string, A to maybe 1A and A to empty string. So this is a complete parse tree because every leaf is a terminal. It has, or at least there's no variables on every leaf. And if I were going to read this, I'd read the leaves from left to right. 1, 0, 1, empty string, concatenated. That is the string 1, 0, 1. That's a complete parse tree. And the reason I picked this parse tree is because it will let me, it lets me derive it to string 1, 0, 1, which can actually be derived separately via a different parse tree. If I do another parse tree, starting with S, again splitting to AB, but then using the substitution rules A to 1A and B to 0, 1B, then AB to empty string. What I get, if I read off the leaves of my parse tree in order, I concatenate 1 empty string, 0, 1 empty string, and get 1, 0, 1. So because I have two distinct parse trees for the string S equals 1, 0, 1, this implies that S is ambiguously derived. And of course, we say a grammar is ambiguous if at least one string is derived ambiguously. So the answer to this teaser is yes. We gave a grammar, we looked at the grammar and tried to figure out, is it ambiguous? To prove that it was ambiguous, all we had to do is find some string with 2 or more parse trees, or equivalently, 2 or more leftmost derivations. It's slightly harder to prove that a grammar is not ambiguous. So far, the only method we know how to do that would be to do so by informal argument. We'd say, okay, well, look at this rule, look at this rule. No matter how you go from here to here, this happens, and therefore you get exactly one derivation for every string in the language. Usually we want to find out the language first. We might talk a little bit more about that later. But proving ambiguity is relatively easy. We just have to find some string. If we can't find some string, the grammar is not ambiguous. I also want to remind us that a leftmost derivation is a derivation, so sequence of replacements, in which we always replace the leftmost variable. So if I were to take my first parse tree up here and write it out as a leftmost derivation, I would start with S, do my double arrow for yields, produces, derives. I think yields is the word the textbook uses. S to AB. And then in my parse tree doesn't tell me immediately whether I should replace A or B first, because, and strictly speaking, I'm allowed to replace either one. My only rules for grammars is that I have to replace one variable at a time. But in a leftmost derivation, I'm always going to replace A first. I have 1OAB. Then I have to replace the leftmost variable first. So I replace A again, 101AB. Then I replace the first A with an empty string, 101B. And finally, I replace the last variable, the B, with an empty string. So we write a double arrow with a star over it to indicate derives. That is, there's multiple rules that take us from S to the string 101. One way to remember the notation with the star is to think of it as kind of like a Kleene star over this little operation yields. There's 0 or more yields taking us from S to 101. So we write yields Kleene star as kind of notation abuse to tell us that, or derives. So that is our teaser. And we will today spend a little time sitting on and reviewing the context-free grammars. So we'll see these definitions again, and we'll continue to do examples to make them more familiar as we go. Before we get started, I have a few announcements. So homework number 3 is due Monday, 11. I wonder where I got 11 from. It says 11 in my notes. November can't come soon enough. Okay, July 19th, 2021 at 11:59 p.m. EST. Oh, that's probably where I got the 11 from. So that's probably today. If you're watching this on Monday, it might be even a day or two ago. So turn that in. Homework number 4 is due Monday, 11/26/21 at the same time, 11:59 p.m. Eastern. Homework number 1 and number 2 are published, and the solutions are up. So you can check those out. We'll try to be a little bit more prompt with the homeworks coming back in the future. We'll try to get homework 3 back to you at the end of this week. Let's see. Oh, there was great feedback. I really appreciate the feedback that you guys put on homework number 2. I've read through all of it, and we're going to try to modify the course slightly to make it better for you guys. So in particular, if you're looking for LaTeX tutorials, you can always come. Let's see. LaTeX tutorials, always okay in office hours. And then also see Ed. Yumin made a great post with LaTeX materials on the Ed discussion board. I've linked it from the course webpage. So that should be a guide. I highly encourage, even if you haven't used it so far, to start trying to pick up LaTeX. It's a great system. We'll try to do more guidance on the sort of homework answers we expect on the homework from now on. And finally, I'm going to be moving one of my office hours. So I'm moving my Thursday afternoon virtual office hours to 5:30 to 7 o'clock p.m. Eastern. So that's in response to people who I know are working on East Coast time and prefer office hours after work. So hopefully that'll work better for more people. Oh, and I do have one last announcement, which is a reminder. Reminder to write up your solutions yourself. So we've seen just a few very similar pairs of homework solutions. That could be a coincidence, and I sincerely hope it is. But we're just keeping track of any pairs of questions that come up that are similar. And if the same pairs of people continue to have pairs of really similar answers, we'll have to reach out and chat about it. So again, it's fine to work with your friends on your homework. You can solve the problems together, but you're not allowed to share written notes. So solve the problems, take your own notes, and then go back and write up the homework solutions by yourself so you have your own work down. Similarly, I want to remind you that reference sites are okay. So Wikipedia, you can look up the Wikipedia definition of an NFA while you're doing homework, but no question and answer sites. So specifically, if you're on Chegg, we will be checking that and keeping tabs. Hopefully that won't become a problem. So that is our big slate of announcements for the day. Today, We're going to start with review, focusing on context-free grammars. Then we're going to introduce Chomsky Normal Form. So this is a standard form for context-free grammars. It'll help us figure out, for example, if two different looking grammars produce the same language, we can reduce them both to normal form, although we won't go into that in very much detail. And then in the second part of this lecture, we will talk about push-down automata. These are very fun and powerful machines. All of our automata so far have been finite, which means they've had finite alphabets and a finite number of states. In other words, the only way a DFA or an NFA can remember something is by essentially storing it in terms of what state it's in. It has an input string that's telling it sort of what to do, and the only way it might have some access to the input it's seen before is in terms of the state it currently inhabits. If it's in a certain state, that's all it knows. And that finiteness has given us problems before when we're trying to count things, or we're trying to measure things, or we're trying to compare things. So our automata will get a lot stronger when we give them larger infinite memory. So push-down automata are automata with a stack memory. So they have a memory that's very much like an infinite stack data structure that they can push symbols onto and pop symbols from. And we'll see that that model of access precisely captures the context-free languages. So push-down automata should be really fun. Okay. So CFG review. So quick notes, things we learned last week. A context-free grammar is a set of substitution rules that turn single variables into strings of variables and terminals. So at its core, that's all a context-free grammar is. It's a bunch of substitution rules. At any point, you've got some string in your workspace. It's got possibly some terminals and possibly some variables. And your next step is to transform one variable into some other string according to a substitution rule. We say that a string is derived, and we use this arrow with a star above it, from another string if it can be obtained by repeated substitutions. Eventually, we'll reach a string of only terminals. The set of all strings that the grammar can make. Set of all strings derived from the start variable is the language of the grammar. This is the natural class of strings that the grammar defines, all the strings you can make starting at the start symbol. Languages described by some context-free grammar are called context-free, naturally. So just as every DFA recognizes some language, every CFG describes some language, like a regular expression. And the class of all the languages described by some CFG, well, those are the context-free languages. So last time we showed some things about the context-free languages. So we showed that the regular languages were a proper subset of the context-free languages. And this was because, well, we know context-free, class of context-free languages is not a subset of the regular languages, because non-regular languages like, for example, this language, our favorite non-regular language, 0 to the n, 1 to the n, for some n greater than or equal to 0. Non-regular languages like that one are context-free. So, there's a grammar that generates all the strings in that language, from which all the strings in that language can be derived. So the context-free languages cannot possibly be a subset of the regular languages. However, the regular languages are a subset of the context-free languages, because any DFA can be turned into a CFG. So we showed how to convert DFAs into CFGs. In particular, we showed it like this. So we showed how to convert DFAs to CFGs. The idea was we simulated the execution of the DFA on a string with substitution rules. So as an example, here were our two rules for converting a DFA to a CFG. Create rules Ri to ARJ for each transition, delta QI A equals QJ. So every time we have a transition from the state QI on the input symbol A to QJ, we'll create a rule in our CFG that sort of does the same thing. It takes a live variable corresponding to state QI and turns it into a variable for state QJ. And it also prints this symbol that we transitioned on. So if we take a bunch of these transitions in a row, we're going to constantly keep up with a particular state, and we're going to be writing down a string of terminals that indicates the string that would move us along our state set. So we'll do an example in 1 minute. The last rule for this construction is we also want to create except rules. So we'll say you can go from the variable Ri to the empty string for each except state QI. So as an example of how this works, let's convert the language W such that W is all strings in 0 star, that is all strings of zeros, such that the length of W is divisible by 3. All right, so we've seen earlier that the following DFA will recognize this language. We'll accept on the empty string, and then on other strings, every time we read in a 0, we will move from Q0 to Q1 to Q2 and back to Q0. Every time we've read a multiple of 3 zeros, we'll be back in the start state. We're in the start state only if we've read a multiple of 3 zeros. So let's see how this DFA turns into a CFG following our rules. So first, we'll create rules Ri to Arj for every transition. So in particular, we have a transition from Q0 to Q1 on 0. So we'll go R0 to 0 R1 for state 1. We'll go from state 1 on a 0 to state 2, from state 2 on a 0 to state 3. Also, we'll create rules going from every except state, every variable corresponding to an except state, to the empty state. So we'll have a second rule on R0 that lets us finish. And now I claim that every string generated by this CFG is a string accepted by our DFA. So if I do a derivation like R0 to 0 R1 to 0 R2, sorry, 0 0 R2 to 0 0 0 R3, let's see, not R3, R0. And then use my second rule to go from R0 to the empty string, I get 0 0 0. Similarly, I can use my first rule, go from R0 to the empty string. Or I can go, from R0, I can derive 6 zeros by effectively going around this loop twice and then convert R0 to the empty string. So I hope you can see that every time I follow a rule in this new grammar that I've built, I add a 0 to my string of variables and terminals, and I increment the variable by 1. So I'm always having one live variable that corresponds to one particular state in my DFA. Whenever I stop, I've gone around this little loop I built in my CFG. And this same sort of construction is going to work for any DFA. We'll just create a bunch of rules that simulate transitions between states. So that is our proof of this statement, that the regular languages are a subset of the context-free languages, and our completion of this picture that tells us the regular languages are a proper subset of the context-free languages. The punchline here is just CFGs have more power than regular expressions, than DFAs, than NFAs, than GNFAs. They can represent more languages than we've been able to represent before. Let's do another example. This will be an example of how we might go about looking at a context-free grammar and figuring out the language that derives from it. So let's consider the grammar G equals V sigma R S. So this time I've just chosen to write my grammar out as a for tuple. I'm going to write a set of rules from which you could sort of back derive the for tuple. But this is what it might look like if I'd written out the grammar formally as a for tuple. And we'll say the variable set is S, which we'll use as our start variable, A and B. The terminal symbol, sorry, the set of terminals contains 1, 2, plus, and equals. These are just symbols. And the rule set is S to 1A2, A to 1A1 or B, and B to plus 1 equals. So the question is, what language does this grammar describe? So let's look at a bunch of ways we could maybe figure this out. Tactic 1, well, of course, we can always just derive some strings. So for this tactic, I'm just going to go through, start at the start symbol, and derive some strings purely at random. You know, whenever there's a choice between multiple rules, I'll pick a rule arbitrarily. Or I could even draw a tree of rules and pick all the rules. That's another way to get a handle on how a CFG might generate strings. I could certainly go from S to 1A2 using this first rule. And then I could go from, substitute this A for 1A1. So get 1, 1, A1, 2. Then maybe I substitute my A for a B using the second rule for A. Get 1, 1, B1, 2. And then substitute B for terminals. So 1, 1 plus 1 equals 1, 2. What's the simplest string I could make? Well, probably S to 1A2, 1A2 to 1B2 using the second rule for S, and then this to 1 plus 1 equals 2. I'm starting to see a pattern here. I've got strings of ones, I'm adding 1 to them, and I'm getting their sum. So if I use the rule S to 1A2, and then I use my second rule a bunch of times, that's why I've written a little asterisk to show that I am deriving, but this is not an immediate yield because I'm using the same rule a bunch of times. Maybe I use it 5 times, 3, 4, 5, 6. Oh man, it's quite a lot. Let's just do a few. Maybe I've used it 3 times. So now I have 1, 1 on 1, A, 1, 1, 1, 2. And then I'll go to 1, 1, 1, 1, turn my A into a B, 1, 1, 1, 2, and then finally turn my B into terminal symbols, 1, 1, 1, 1, plus 1 equals 1, 1, 1, 2. So now I have a pretty good idea of the sort of strings that this grammar produces. But I'll show you another tactic that we could use. So tactic 2 is simplify the grammar. So in this case, we can observe that B goes only to terminal symbols. Right? Whenever I see a B, there's only one rule I can use. B will turn into this string plus 1 equals. So I can actually go back and substitute this string plus 1 equals in for B and create a simpler grammar. I can say S always goes to 1A2, and then A goes to 1A1, or it goes to B, but B always goes to plus 1 equals. So now I have 2 rules, and maybe it's easier for me to see with only 2 rules going on, precisely what's happening here. I always generate a 1A1. The only variable here is how many times I use this first rule, A to 1A1, before I finish the string by putting in +1 equals. So those are 2 ways of getting some intuition for this language. A third way, I could draw some parse trees. Sometimes these are even more helpful than derivations for seeing the structure of what's going on. So in particular, I start with S, and then maybe I go to 1A1, and then I go to 1A1. Oh, sorry, S goes to 1A2, doesn't it? It's always a 2 at the end. And then A goes to 1A1, and then A goes to B, which in turn goes to +1 equals. And if I draw out a few of these parse trees, and I start concatenating them to get strings in the language, not only do I get some example strings, like I do from my derivations, but I also sort of see the structure that every parse tree is going to have. Every parse tree is going to follow, it's going to use this first rule to go from S to 1A2. Then some number of times we'll use our second rule to go from A to 1A1. And then we'll always finish off with this third rule. So that is an example of what I might do if you threw a random grammar at me, like I might ask you to do on the homework, and asked, what language does this grammar describe? How I would start to get a handle on it, how I would think about it, and then how I would test my answer. In particular, in this case, I'm going to write the answer as a regular expression because this is a language that can be written out as a regular expression. All the strings that come out of this language are going to look like n1s plus another 1 equals n minus 1 ones and then a 2 for some n greater than or equal to 0. I'm sorry, I said a regular expression. This is sort of like a regular expression, but strictly speaking, this is actually not a regular expression because I'm plugging in an arbitrary n here, and these two things are linked. It's not a regular language. So I take that back. But this is a representation of the language that gets generated. Don't get confused here. This 1 to the n minus 1, this is not a math. This is not 1 to the power of n minus 1. This is just 1 repeated n minus 1 times. It's always what our exponent will mean. And remember, we have no idea of math. All we're doing is writing symbols down on paper. You don't need to know any math at all for this class. You just need to be able to follow instructions in detail. That's not true. Okay. So that's an example of how we might look at a grammar and figure out what language it recognizes. We also saw another design trick. And I want to emphasize this because I think this is also going to be relevant for the homework. How to build a CFG, context-free grammar, for the union of two languages. Well, suppose we have G1, a grammar for L1, and it looks like this. S1 to some other stuff, and then a bunch more rules. And we have G2, a grammar for L2. And it looks like S2 goes to some symbols, and it has a bunch of other rules. I claim if we add the new start rule, S goes to S1 or S2, we get a grammar that recognizes L1 union L2. All right. And the reason I claim that is just because no matter what happens, if I start with the symbol S and then I go to S1 or S2, and all the other rules are copied from grammar 1 and grammar 2, then I know that the string I get out is going to be an L1 if I start with S1, and it's going to be an L2 if I start with S2. So I can generate all of the strings in L1 or L2, and I can generate only those strings because all my derivations are going to go through S1 or S2. So I could write this formally if I wanted to as a for tuple. If I had G1 equal to V1, sigma 1, R1, and a start symbol S1, and G2 equal to V2, sigma 2, R2, S2, then G3 is the union of the variable sets, the union of the terminal sets, the union of the rule sets, plus my new rule, that is S to S1 or S2. Oh, and I suppose I also need a new variable here. So I'm going to add to my variable set a new start variable and make that my start variable. So I have this new grammar. It's still a for tuple. And I claim G3 recognizes L1 union L2. So that's a trick for building a context-free grammar for the union of two languages. And I'll tell you, there are tricks for star and concatenation and other things as well. And you'll see these on the homework. That's all I'll say there. So that's our rapid review of the CFG stuff we did last time. I also want to introduce one new concept related to CFGs. We won't go into too much detail, but I do want you to know that this concept exists because I think it's comforting. So 2, Chomsky Normal Form. I think I mentioned this linguist guy, Chomsky, in passing last time. He's done a lot of fascinating work. He's worth looking up, and I think he did invent this form. So suppose we have two different looking context-free grammars that generate the same language. And just to convince you that that is possible, I'll show you a simple example. Suppose we have a start symbol S that goes to 0S or A, and then A goes to A1 or the empty string. Now I claim that we'll do this first rule some number of times. So from S, we'll go to some number of zeros followed by S, and then eventually we'll go from S to A. Then we'll do this second rule, A to A1, some number of times. So after some number of rules, we'll have some zeros, an A, and then some ones. And from there, we will go from A to the empty string. So we'll end up with a string that looks like some zeros and some ones. And I claim that by repeating these rules the right number of times, I can generate any string made up of a substring of zeros and a substring of ones. Now, here's another grammar that generates the same language. And again, we'll start with S. We'll do this first rule some number of times. We'll end up with S111 or something like that. Then we'll turn the S into an A. We'll generate some zeros. And we'll end up with some number of zeros followed by some number of ones. So I hope I've convinced you that you can indeed have two different looking grammars that generate the same language. And this raises a really natural question, which is, how do we tell if two grammars recognize the same language? And the answer is we define a standard normal form. So the intuition behind a normal form is simple. You've got some mathematical objects that have the potential to look superficially different, even if they're the same. So you have a procedure or a normal form that you define for all of them, along with a way to reduce the thing down to the normal form. So example, fractions, I think, is a good example. Suppose you want to know whether 24/18 is the same as 8/6. These fractions are not reduced, so it might not be obvious. It's a little bit hard to tell. However, if you divide the first one if you divide both the numerator and denominator by 6, and you divide the second one, numerator and denominator, by 2, you find that they are both equal to 4/3. These two fractions are equal, and we know that because we had a standard form to reduce to. Both of them are going to boil down to the same simplified fraction. And that's the same idea that motivates the normal form for context-free grammars. We want one form. That does precisely this. So definition: a context-free grammar is in Chomsky normal form if every rule has the form A goes to BC, or A goes to A, where A, B, and C are variables, and A is a terminal. So that is, every rule should be one variable going to two variables, or it should be one variable going to a terminal. All right. So if we took our languages up here, here's an equivalent grammar in Chomsky normal form. Perhaps we go from S to AB, and then A goes to 2 A's, or it goes to 0, and B goes to 2 B's, or it goes to 1. So in this case, this grammar is now in Chomsky normal form because every variable either goes to two variables or it goes to one single terminal. And you can see why this would produce some number of zeros followed by some number of ones. I'm actually there's a couple little addenda that I want to add to this definition. You can also have the special rule S to empty string. So I want to make sure I can generate the empty string if I want to. In fact, I want to make sure S can go to 0 or to 1 as well, because I want to have those single strings be possibilities, right? I don't always want to have zeros and ones. We can also have this special rule. S goes to the empty string, and we have a special requirement. Which is that the start variable is only allowed to appear on the left. So I'm not allowed to have my start variable on the right, and that's usually actually a fairly simple thing to ensure. Just checking my work here. I think we also want to have a couple of rules, BB and AA. We end up with a long first set of rules just to make sure we can get all of the possible combinations of zeros and ones. But this conversion is not the most important thing right now. The important thing, since we're not going to use Chomsky Normal Form much, is the high-level takeaway. The takeaway is that CFGs have a nice normal form. And see the end of section 2.1 in the text for more details. There's a very nice proof of how you can transform any CFG into Chomsky normal form. And that theorem, every CFG has an equivalent in Chomsky normal form. So that particular transformation is not going to be required knowledge because we're not going to dwell on this very much. I just think it's a cool topic, and I wanted to make sure you had that entryway. So if you want to go into that, please feel free to do so, and please feel free to email me with any questions. In this lecture, however, we have to move on. We have to talk about new stuff. In particular, we have to talk about automata with stacks. Push-down automata. So I'll see you in the next part for that. I'm looking forward to it. Bye for now.